All right, I see you've made it alive this far. Okay, we're on now part 2 of 3. So, to reference one of the few questions we had, we're 2/3. All right, at the end of this section, we'll be at 2/3 of the way through. If you divide 3 into 2, multiply it by 100, you'll know at what percent we are. So, let's move forward. Usual concerns. Again, our purpose is to make sure you get through this exam. This is progressive, especially this part. What we're going to talk about in section 2 is mostly electricity. Now, electricity is everything in our industry, HVAC industry, HVACR industry. You know as well as I do that the hotshots in your company, the really good guys that have been doing service work for a long time, are probably the best servicemen you have. They can wire anything. You give them a transformer and a relay and a double pole, double throw relay, and they can change the direction the world spins in. When you wake up in the morning, the sun will be rising in the west and setting in the east. These are the guys that have shown their mettle by that ability. And it's very important because we deal not only with line voltage devices, but we have to control them very often with low voltage control circuits. So we have to be capable of a lot of what an electrician is capable of, with the additional information relative to control circuits that electricians don't normally get involved in. Have a pocket calculator handy. We're definitely going to hit some calculations in this section. User assumes all liabilities. Again, we hope you understand what it is we're saying. We encourage you to take other courses relative to the same information we're talking about here, but we can't control how you apply it in the field. So do be cautious for yourself and the sake of others as well. So let's talk about electricity. Electricity is the flow of electrons through a conductor. That's all it is. Turn on a light switch, the light lights, because of the flow of electrons. Well, what the heck is an electron? Well, to know what these are the electrons, but to know what they are, we have to look at atomic structure. So let's look at a gas. This is one of the lightest gases, I think the actual second lightest gas, helium. Helium, and all atoms are built this way, but I'm just doing this for simplicity. Helium, all atoms have what they call a nucleus, or a center, a core. And in the nucleus is, in this case, two protons positively charged and 2 neutrons which have no charge. They just add mass. They're neutral. Now, so you essentially have a positive element here. And what revolves, if you will, in circles. Remember about atoms. No one's ever seen an atom. We know how it works. We know the effects of it. We can do things to it, throw protons at it, and watch it divide and create atomic bombs and all this stuff. But we've never even seen one under a microscope. So anything like this you see is just theoretical. But if this is positive and it has mass, and this is negative and it's smaller, then there's a heck of an attraction, because opposites attract. All right? It's essentially a magnetic model that kind of looks like the universe. You know, this is the sun and we revolve around it and all that jazz. So you can understand where this came from, but it serves, and don't worry about this detail. I'll tell you when it's important. I just want you to get the broad strokes. It's important to understand that this is simply a model that explains how the electrons flow. Let's look at an electron. First of all, that's the diameter of it. Pretty small, 0.22 inches. That's awfully small, okay? Let me find my cursor, there it is. It weighs 0.00009 grams, okay? Not grains, grams. That's pretty light, okay? It's small and it's light, but it moves at the speed of light, 186,000 miles a second. I think that's 7.4 million miles an hour. That would be going around the Earth, the broad end of the diameter of the Earth, 7.5 times in 1 second. That's how fast it's moving. Speed of light, you can't see it. And according to Einstein, nothing moves at the speed of light. If it did, it would create a mass problem. We'll get into that. Anyway, if you count at any point, draw a line, and start counting the number of electrons that flow through that point. And if you count, and we have to use exponential here, 6.24 times 10 to the 18th power. That means this number with 18 decimal places. So that's 6, I don't know, gazillion, 240, humping million, whatever that thing is they call it. Down here I'm comfortable, millions, so on. But if that number flow in 1 second past 1 point, then we call that a coulomb. All right, after the guy that invented this, that came up with these numbers, not invented it, but realized the numbers. And nowadays we call that 1 ampere. So when 1 ampere has flowed, if you will, then at some point in time, 6.24 times 10 to the 18th power electrons have passed that point in 1 second. What if 10 amps are flowing? Well, 6.24 times 10 to the 18th power times 10. So it's to the 19th power. Okay? That's how it works. That's what it is. Now, why is that important? Well, this is a copper atom. A little more complicated. Look at this nucleus. Massive protons, neutrons, they all have to equal. If they don't equal, then it's, the number in here have to equal the number out here. If they don't, it becomes unstable. But look at this. You got 1, 2, 3, 4 rings. And if this is the sun, we're in the third ring. We're the third rock from the sun, and we're revolving there. Now, but look at this fourth ring. This electron here is called the valence electron. It's in the valence ring. It's all alone. Its attraction to that positive core, that nucleus, is very slight by comparison to this one, which is very strong. So this one becomes the promiscuous electron that's going to leave that copper atom and go to the next copper atom. And what happens? It happens instantaneously. Remember, this is happening at the speed of light. We don't know. We're just saying it does happen. The moment this leaves, this ain't copper anymore. It's some other metal, probably, that has 27 instead of 28 electrons. All right, so it has to be replaced immediately. And scientists can see, nuclear physicists can see it leave, they can see it replaced, but they can't find either electron anywhere in between. That's called the quantum leap. It's very small, from electron to electron. Remember, you could take 500,000 of these copper atoms and put them side by side, 500,000 of them, 500,000, and they would hide behind one human hair. That's how small this is. Okay? So this electron leaving, being replaced, keeps us a copper atom and causes electrons to move. And that's electricity. We have excited the material that it's moving within. All right? Let's make, I call it the great water analogy, because it is a great analogy and because it is repeated ad nauseum. And for good reason. If you take a look at this water tank, and I got a pressure gauge at the bottom of the tank, and I fill the tank up with water. As the height of the water in here increases, the pressure in the tank increases. In fact, for every 2.31 feet, 27.72 inches of height in water, I'm going to have 1 pound of pressure. If I double that, I'll have 2 pounds. If I have 10 times that height, I'll have 10 times that pressure. I'll have 20-some pounds of water. All right, so in this tank, I have 2 things. I have water and pressure. Now, what's going to happen when I open this valve? Well, now the pressure in this tank is greater than the pressure out here in the atmosphere. So Mother Nature says high must go to low. And when I open that valve, the water pressure will push the water through the system. Same thing happens here. This is an AC generator, alternator, however you want to look at this. Don't get hung up on that. All right? It's not important for the exam. This thing makes electrons. Like this holds water, this holds electrons. And it revolves, so on and so forth. Now, when this thing is filled with electrons, like this is filled with water, I have 2 things in here also. I have electrons and I have voltage. because voltage is considered to be electrical pressure. Okay, the water is the same as the electrons, and when I connect this switch, what's going to happen? The electrons are going to flow to wherever they're going. They're going to come back again. No different than if I had hooked this up to some kind of piping and pump system and put the water back in it again. But the pressure inside this generator is what we call voltage. When I say I have 240 volts, I have 240 pounds of pressure, electrical pressure, to do work with. Now, you know 240 volts will knock you down a whole lot quicker than 120 volts will. And 24 volts, you won't even know you're feeling it because the pressure is so slight. So if you think of voltage in that term, it helps you to understand this flow of electrons we're talking about. Because the flow is happening within the conductors, just like the flow, and you can't see it, just like the flow is happening inside a pipe filled with water. But you can't, if you're looking outside of the pipe in a basement, you don't know if there's, what the heck's in there, water, air, gas, what? It's a galvanized, malleable pipe running through the basement. So they're very, very similar in that regard. And of course, the resistance that the piping offers to the water is the same as the resistance the system offers to the flow of electrons. And the greater that resistance, the less electron flow you're going to have. So the voltage pushes the electrons through the resistance in the conductors, as water pressure pushes water through the resistance of the piping in a water system. Okay? Now, if you're working with a boiler at 20-pound pressure and you got a 3/4 inch pipe, you're going to handle about, at proper velocity, you're going to handle about 3.5 gallons of water a minute. That's all you can get through that pipe at the proper feet per minute velocity, feet per second velocity you want. Now, if you want to increase flow, you got to make the pipe bigger. If you want to go, you want 4 times the flow, you want to go from 3.5 to 14 gallons a minute, you need a bigger pipe for the same pressure and the same temperature and so on and so forth. It's the same here. NEC says you can put 18 amps, gallons per minute, amps, however you want to look at this, 18 amps, which is current, okay? Amperage is current. 6.24 times 10 to the 18th power is 1 amp, okay? 10 amps through 18 gauge wire. I wouldn't want to do that, and of course it certainly depends on the voltage. But if you want to quadruple that to 40 amps, then you need an 8 gauge wire. And as the gauge gets smaller, the wire gets thicker. All right, it's a inverse relationship. All right, so it's the same as the water again. Make the pipe bigger, make the wire thicker, you can handle more electrons. Okay? It's like having a 5-lane highway. It can handle 5 times the traffic a 1-lane highway can. And all the little cars on the roadway, they're the electrons. Let's talk about an ampere, an amp. And that's what we do. We call it an amp. We shorten everything in this business. The symbol is capital A. It's a unit of electrical current flow. We know exactly what it is, 6.24 times 10 to the 18th power electrons. Don't remember that number except to impress somebody. It's not going to be on the exam. What's important is that you know what is happening so you can intelligently answer questions on the exam. A milliampere, small m, capital A, milliampere, is 1/1000th of an amp, or decimally 10 hundredths thousandths, 0.001 ampere. To give you an example of how small that is, a typical light bulb takes about 1 amp of power in a house, you know. All right, so that's 1/1000th of that. Okay, that's very small. Milliamps, we use that all the time. You do commercial work, you'll end up with a 4 to 20 milliamp, motor at some point in time. 1 microampere. All right. Now you see this thing that looks like a U with a tail on the front. Okay, that's the Greek letter mu, mu. LMN. In Greek, it's lambda, mu, nu, xi, omicron, pi, rho, right through the whole alphabet. But this one is M, and we use that for micro. Now, a micro anything, in this case a microamp, is 1/1,000,000th of an amp. Tenths, hundredths, thousands, 10,000, 100,000, millions. Okay? 0.000001. That's really small. Where do we use microamps? Heck, we use microamps all day long. We use microamps for every flame sensor, probably most flame sensors you're going to deal with. You know, you want 4 microamps or 5 microamps out of that flame sensor. That's the signal the electronic circuit board is looking to prove the flame. But it wouldn't matter if it was a capacitor, and that was microfarads, whatever. It's micro. Micro anything is 1/1,000,000th of something. Milli anything is 1,000th of something. Why am I telling you this? They're going to ask on a test. All right. Now, let's get some basic stuff working here for electricity and how it works. Here's a basic principle in electricity. Whenever current, electrons, all right, here's a good way to picture the electrons. Sand blasting. Because there's a billion little particles in there, and they're moving really fast. You know that if you ever put your hand in front of a sandblaster that was operating, it'll take the skin off of it. It actually takes the skin off of concrete and things like that that have become encrusted with weather, mold and that kind of thing. So think of it that way, it might have more relevance to you. So whenever these little particles of sand, these electrons, flow through a conductor, and a conductor is anything that will allow current to flow through it, a magnetic field is set up around that conductor. And we use that magnetic field in everything. Every solenoid, every gas valve, every relay, every contactor, every transformer uses this magnetic field principle. Plug this into a wall, hook it up to a load, a motor, I don't care, and you will see, in fact, if you can do this, this would be really instructive. If you have a compass, plug some simple device into the wall, but before you do that, split the cord. Because remember, this is alternating every 1/20th of a second. You know, you have a full alternation in 1/60th of a second, 60 cycle current. So this is going this way and that way. If you have these two wires together, they're going to cancel each other out, and you're not going to be able to see the magnetic field. But split the cord and something you don't care about, a little desk fan or something. Plug it into the wall, and take a compass and just hold it right up against either one of these wires, and you'll see north line right up with that wire, or perpendicular to the wire, I believe. You know, I honestly forget, but it'll either be straight up and down or parallel with the wire, but it'll slam, it'll go right there no matter what direction the compass is pointing in. Well, the compass is affected by magnetic fields. It's a magnetic compass. It's looking for magnetic north from the Earth. And that's what's happening here. In fact, if you were to take a magnet and look at the magnet relative to metal collection, like let's say we're cutting and threading pipe, the slag that ends up in the bucket or the box underneath the pipe threader, if you were to throw a big bar magnet in there, you would see all the slag line up like this, north to south. What you're looking at there are the magnetic flux lines from that magnet. And in this case, the magnetic flux is creating a magnetic field around that you can't see because there's no metal there, no metal slag, but you will see when you hold the compass up there, or you will see when you hook up your amp probe, your clamp-on amp probe. Because the clamp-on amp probe doesn't count the number of electrons that pass that point. What it does is read the intensity of the magnetic field. Because the more electrons that go past that point where you've connected that clamp-on amp probe, the more that pass through there, the greater that magnetic field is going to be, and that needle is going to swing left or right depending on the intensity. And that's all a clamp-on ammeter does, is read the intensity of that magnetic field. In fact, this is what it looks like if you do this. This is an actual picture of slag, metal slag, and somebody threw a bar magnet in it, and you can see the slag line up. Now this is iron shavings, iron slag, so iron is very, very affected by magnetic fields. It becomes a media for magnetic fields. And you can see it actually line up like this. Now, the further away you get from that magnetic field, the less likely the slag is to line up. But the closer it is, the more you're going to see that magnetic field. That's what you're reading. Another principle. If a conductor, piece of wire, conductor, is passed through a magnetic field, a current is induced in that conductor. If you have a big magnet like this at home, take a piece of wire with the insulation on it and hook up your DC voltmeter here and here. Doesn't matter about polarity. And move the conductor. And when you move it this way, the needle will move that way. And when you move it this way, the needle will move that way. It'll peg back and forth, left and right. You're creating, and then you're inducing a current in the conductor by moving it through a magnetic field. What's current? Electrons. You're pushing electrons through that conductor from this point to that point because you moved it through a magnetic field. Likewise, if the magnetic field is passed over the conductor, a current is induced, again, in the conductor. Do that. You do that, the needle will move this way. When you go back here, the needle will move the other way. That's the way it works. And you're inducing, in this case, a simple, low, extremely low voltage DC current. Okay? It's going to have it's a low current. It's going to have a low voltage pushing it. So, this brings us to transformers. Why are we talking about transformers? Because a transformer is a big old magnet. When you look at a transformer, basically it's built like this. This side gets plugged into the wall. And what you do is you wrap, and I'm showing it wrapped around, right around this iron core that I made very conveniently here. But what it is, it's a wrap of like a winding on a motor, just in proximity to that iron core. Because the iron core is going to intensify the magnetic field that's going to be set up here. So this is the one winding. The other winding, in this case, it's a step-down transformer. We have fewer turns in it. But it's not connected physically to anything. This wire is all insulated. There's no continuity between this point and that point. All right? Now, look at this. I think it's a Honeywell AT72D transformer. And you know when you pick this thing up, it weighs 50 pounds, it seems like. All right? Because it's iron. This mass here, this block is iron, but it's not one block. Look at it carefully when you pick up a transformer. It's maybe 16th-inch slivers of iron that are bolted together. Why that? Well, if you have a block, you only have 5 or 6 sides that are surface area. If you have slivers, then you have that times the number of slivers you have. So you have increased surface area, which increases the magnetic field. The winding you plug into the wall, we're going to call the primary winding, and the winding that doesn't get plugged into the wall, or gets the induced current, is going to be called secondary winding. If I plug this into 120 volts, this becomes a step-down transformer. And only because I have fewer turns over here than I have over here. Remember, when current flows through a conductor, a magnetic field is set up around that conductor. And if you have alternating current and you keep changing the direction, you keep changing the direction of the magnetic field. It goes that way, then it goes the other way. And what will happen if you have 5 turns here, and this is a very common number for residential step-down transformers, if I have 5 turns here for every 1 turn there, then I have a 5-to-1 turns ratio. And my resulting current is going to be my input, 120 primary, divided by the 5-to-1. I can expect to see, if I read 120 volts here, I can expect to see 24 here. I divide the primary voltage by the number of turns, and I get the secondary voltage. That's the rule. That's the way it works. It works that way every time. If you assume this is 120 volts and it turns out to be 115, that's why you didn't read 24 volts here. You have this actual reading divided by the number of turns will give you the secondary. All day long. So, what size transformer do you need if you have, let's say, 2 zone valves Each are 24 volts, and they both draw 1 amp. Okay? How big does your transformer have to be? Oh, 40 VA. We use 40 VA anytime we have 2 zone valves. In fact, you can put 3 zone valves, not when they draw 1 amp. Here's the formula. The VA of that transformer, the volts times the amps of that transformer you need, is the volts times the amps times an inrush factor of 1.2. That's 20%. Inrush is low voltage lock rotor current. When you have a compressor motor that draws 20 amps, except when it starts up, it draws 80 amps, 80 to 100 amps, 4 to 5 times the running amps. That's lock rotor current, because you're taking that big, powerful motor from a dead stop, lock rotor, to speed. And to do that, you're going to have a heck of an increase in current, or VA. All right? And that results in a current draw that's very high. It's 4 to 5 times the running load. So your 20 amp motor is going to draw 80 to 100 amps for a few seconds while it gets up to speed. In the case of 24 volt circuit, it's not 4 to 5 times, it's only about 20%. So inrush current is always greater than running current, and in this case by 20%. So what's the formula? Volts times amps times 1.2. Well, they're 24 volt motors, there's 2 of them at 1 amp each, times 1.2, 57.6 VA. So run out to the truck. Don't pick the 40 VA transformer. It ain't going to work. You know when it ain't going to work? When both valves are trying to open at the same time. Because then you got a 2 amp load on that 40 VA transformer, and you need a 57.6 VA transformer. So go find that 57.6 VA transformer and bring it back. Good luck finding it. Let's talk a little about alternating current. First, by definition, alternating current is an electrical current. Remember, this is electrons. An electric current that reverses its direction at regular intervals. Where we live in the world, and most of you live, is what we call 60 cycle current. That means that, and we're looking at, this is a voltage sine wave, but let's ignore the fact that there's an amperage associated with this for right now. Let's just look at the pressure. We go from 0 pounds per square inch, 0 volts, to a positive 120, back to 0, to a negative 120, and back to 0 again. And all that happens if this is 60 cycle current, 60 hertz current, because hertz has become synonymous with cycles per second, named after the gentleman, again, who did all the discovery and calculation work. That all happens within 1/60th of a second. So within that time period, there's 2 alternations. You go from 0 to positive, to 0 to negative, back to 0 again. It changes twice, changes direction twice. And negative doesn't mean somehow it goes negative. All it means, all this is trying to show you is that this is going in this direction. Consider a 360-degree wheel on the generator, the alternator that made this thing. This is 1/2 of a revolution. This is the other half of the revolution. So it's going from 0 to positive, back to 0 again, and then at this point in time, the electron flow actually goes the other way. If it was coming this way, it stops dead and goes back the other way. And it builds to 120 pounds of pressure, voltage, however you want to look at this, back to 0 again, and then fades out. So this is the peak, and that's the peak. And when you hook up a voltmeter, what do you read? You read the peaks. You can't see all this. This is happening in 1/60th of a second. This is alternating current. It alternates. That's how that happens. Both line voltage and low voltage. Direct current, DC current, is electricity in which all electron flow is continuously in one direction. Essentially, it's flatlined. All right? It's one direction only. Let's look at Ohm's Law. Don't go running into the street. There's some certain things, I know everybody gets turned off of Ohm's Law, but there's some real good practical applications for Ohm's Law in the field, and you need to understand the principles. You really do. When you sit down to take this exam, they're going to give you a piece of blue paper. On one side of it, it's going to be blank, the back side, obviously. On the front side is going to be a place where you can make comments about the exam. It's optional. Do not take time to do that until your exam is finished and you've looked everything over and you're happy that you now satisfied the requirements, and now you can criticize, comment on, congratulate, whatever you want to do, parts of that exam. And that's the piece of paper that they give you to do that. The NATE Technical Review Committee, the people that put this program together, are looking at those things. They want to know what you think. So if you have the time to do it, do it. It's strictly optional. But the back of that piece of paper, the blue piece of paper, is for you to make notes, whatever. Whether you use that or not, you have to hand it in. Even if you've done all kind of math problems on the back of that piece of paper and you haven't filled out the front, it has to be handed in. Every piece of paper they give you has to be returned, including the envelope, the sealed envelope they give you that everything is in. You're going to destroy it opening it. It has to be returned. That's the way proctored exams are done. If any one piece is missing when you bring it up to the proctor, he's not going to accept it. And you ain't going to get credit for the exam. So make sure you keep everything together. Anyway, when you sit down in the back of that piece of paper, you want to do this. E over IR. I don't care if you're doing a circle, triangle. You don't need a shape. Just put E over IR. That's Ohm's Law. E equals IR. E is electromotive force, or what Sir George Ohm called electromotive force when he first discovered it, EMF, is voltage, we know and love today. When you see E in technical literature relative to electricity, it's voltage. When you see I, it's intensity or inductance. That's amperage. This is 6.24 times 10 to the 18th power electrons is one of these, one I. R is a resistance, usually in ohms. Suffice it to say ohms or impedance, whatever. This is important to write down this way because you're going to forget it. And they're going to give you a question that's going to confuse you. How do you learn this? E equals IR. E equals IR. E equals IR. How do you, just by what I did. You walk around the house, you go E equals IR. You talk to your dog. You talk to your children who don't understand English, and as long as you can hold their attention, that's important. You say it to yourself over and over again because it's meaningless. It's a formula, and that's the only way you're going to remember it. E over IR. And what are you going to use this for in the back of that piece of scrap paper? When they say solve the voltage, what is the voltage if I have this amperage and that's that resistance? What are you going to do? E equals I times R. So E equals I times R. What are you going to do when they say, what is the resistance when I have a 240 watt electrical element and it's drawing 13 amps? What's the resistance of that element? Well, if you're solving for the resistance, you're going to take the amperage and divide it into the voltage because it's E over I. You see? If they want to know what the amperage is, and they give you the voltage and the resistance, move the hand over here, divide the resistance into the voltage. You get the amperage. You see? That's how you're going to use this. You can do it in your mind, but you got to remember E is over IR. Alright? Now, just some things about this. And this is not on the exam, but I can't talk about this, Ohm's Law, without telling you this. Ohm's Law does apply to three-phase circuits, but you have to multiply your voltage by 1.73. 1.73 is the square root of 3. So your voltage in a 240-volt three-phase circuit is not 240 volts for this calculation. It's 240 plus 73%. All right, the square root of 3. Also, again, for your own reference, you can't solve for resistance on inductive loads using the Ohm's Law. Ohm's Law only works for strictly resistive loads because there were no inductive loads when this was developed, not back in Sir George Ohm's day. You cannot apply Ohm's Law for resistance to AC inductive loads. What's an inductive load? Well, There's two kind of loads in our world, essentially, inductive and resistive. We get into capacitance and all that too, but don't bother with that stuff because it's important to understand the principle, but it doesn't have any value in the real world. An inductive load is an AC electrical load in which the voltage reaches its peak before the current. Capacitance can change that, but suffice it to say, in a purely inductive load, the voltage reaches its peak before the current. Inductive loads use magnetic fields, such as motors, solenoids, those kind of things. They use inductive fields. If it moves, it's probably inductive. That's a very good statement. I didn't make it up. I read that somewhere, and I just remembered it because it made a lot of sense. If the device moves, it has an inductance attached to it somehow. Well, what's that look like? Well, graphically, it looks like this. If this is my power source, this is my inductive load, and I have a resistance there, or if this is my inductive load, whatever, what you'll see on a purely resistive load is this. Your voltage, your amperage, your power, everything peaks perfectly at the same time. That's purely resistive. Here's E. See E? Follow that up. That's voltage. I don't know which peak that is. Then you'll see current in here. Here's your current. That's easy to see where that is. And the other one of these two is, it's got to be VA. It's always higher. So this is your power. That's your watts, voltage, and amperage. They all peak at the same time. Resistive load, you turn the toaster on. This is what you get. Voltage, amperage, VA, they all peak together. The toast is done. It pops out. They all go to zero. Current flow is, doesn't matter whether it's alternating or direct. This happens. Inductive load. Holy cow, looks like this. Take this one phase here. Here's inductive. Now here's your voltage. And we said it peaked before the amperage. Here's your amperage line. CI? That's your amperage line. So the voltage peaks. This is time. Remember, this is 0 minutes, seconds, whatever, and this is positive seconds. So the voltage peaks, the amperage peaks over here, and the power, the VA, peaks at some point in between. Because this is that multiplied by this. All right, so this is cattywampus. This is skewed. This is something is getting a peak before something else does, and that drops low, and then that peaks. The other thing peaks. So that's inductive load. It's moving something. So, brings us to the next part of Ohm's Law we want to deal with, and that is pi. Now, you'll see all the textbooks say P equals EI. Well, this spells pi, and that's a whole lot easier to remember. And whether you multiply this by that or that by this doesn't change a thing. All right, so I put it this way. This is the other thing you want to write down on the back of that piece of paper, the blue piece of paper. You're going to write E over IR, and you're going to write pi, P over IE. That's not hard to remember. When they say solve for power, watts, what are you going to do? Multiply volts times amps. When they say solve for amps, you're going to divide the voltage into the power. Same caution here. Three-phase power, multiply E by 1.73. That's volt amps. That's what power is, VA. How do you get the VA of a transformer? Well, you multiply the volts times the amps times 1.2. That's your VA that you need, volt amps. 1 watt, remember, is equal to 3.413 BTUs, and 1 kilowatt, K is killi, thousands, not thousandths. Thousandths would be milli. Killi is times 1,000. All right, so 1 kilowatt, 1,000 watts is equal to, move it 1, 2, 3 decimal places, 3,413 BTUs. Why am I telling you this? They're going to ask you that in the test. Power factor. They're also going to ask you about that. What the heck is power factor? Well, let me explain it this way. Power factor is the ratio of real power to apparent power. Why do we care about that? Well, power factor is going to tell us how efficient our power is, or a given circuit is, or a given motor, or whatever the case is. Real power, now this is a ratio, so it's a fraction. What do you do with fractions? You divide them to find out what the percentage is, right? Good, that's where we're heading. Real power is the actual power being used by a circuit. How do you know what that is? The actual power. Put a wattmeter on it. What's apparent power? Apparent power is derived from Ohm's Law. It's volts times amps. Read the voltage, read the amperage, multiply one by the other, and that's your apparent power. The real power is what you read with a wattmeter. In this case here, this is, remember, the resistive load? My power factor is 1. It's perfect. Look at that. Everything peaks together. No problem. Over here in my inductive load, it's going to be less than 1 because I get this huge surge in voltage. Then I get this huge surge in amperage that don't line up with each other. And the power, the actual wattage is higher. Of course, because it's volts times amps. So what do? Well, here's what you do. You come up to this unit, circuit, whatever it is. You read the wattage. And then you divide that by what you read in volts times amps. And that will give you the power factor. And where does the power factor get applied? Well, if you want to know what the real wattage is on a device, you have to multiply the amps times the voltage times the power factor. And this will be a decimal. It'll be like 0.92, 0.78, 0.89, something like that. This will be a correction for the volts times amps. And that will give you the actual reading. Diode. Well, diode's a funny thing. It's got a cathode and an anode. Don't worry about that. They're not going to ask you that. But it looks like this. And what it does, it's a solid state device that we use on all our circuit boards that will conduct current in one direction only. And of course an electrical engineer made this up, and those guys are funky to be kind. It goes backwards. That is to say, current flow, when you look at this on a plan, is in that direction. Alright, now I'm sorry, I'm stupid, and that's a great big arrow, and it's pointing to the right. Why is the flow to the right? You know, it's just, know that when you look at a diode, the current is flowing this way. A diode becomes a conductor in this direction and an insulator in this direction. This is the wall, and maybe going back in history, I don't know, that's why they did it this way, to tell you where the current stops. I guess it's a matter of the glass being half full or half empty. But this will be asked of you in the exam. What does this thing do? Well, it only allows current to flow in one direction. Current comes in this way. If this is alternating current, it can't go back the other way. This diode, this solid-state device, will prevent that from happening. If you take 4 diodes, take 2 pointing to the right, 2 pointing to the left, and wire them in parallel, you have a bridge rectifier. Now you can take AC current and convert it to DC current. But don't worry about that either. Understand this principle. Series circuits. Let's talk about series and parallel circuits. Let's concentrate on one at a time. This may seem like basic stuff you did. I'm sure you have another word for it, way back in trade school or whatever. But it's really important in our business. You have to know a series circuit from a parallel circuit, and you have to, more importantly, know what the effects of dealing with these circuits are. Just for basics, if I have this is my bad impression of a sine wave. If this is a 120 volt power source and I have 3 resistances of different values in series, then what happens to the amperage? What happens to the voltage? And why is that important? Well, here's the rule. The voltage is divided. In a series circuit, this is not true for parallel. In a series circuit, the voltage is divided across each of the different resistances relative to the value of the resistance. 10 ohms, 20 ohms, and 30 ohms gives you a different value. What I'm saying is this 10 ohm resistor, if this is 120 volts and you put a voltmeter across here, you're going to read 20 volts. How do I know that? Ohm's Law. That if you put a voltmeter across this, even though here you would have 120 volts, this is only going to be 40 volts, and you're going to have 60 volts across here. But 60, 40, and 20 is 120. It always adds, but it divides across each of the loads. The total current flows through each resistance. There's only one current value, whether you measure it here, 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 doesn't matter. You're going to read in this circuit 2 amps. The resistances are added together to get the total resistance. It's R1 plus R2. So if I add 10, 20, and 30, I'm going to get 60 ohms of resistance. That's what happens in a series circuit. And what they're going to ask you about specifically on the test is what happens to the voltage and the amperage. How does that handle? Why is this important? Well, let's give you some relevance here. AC loads, AC, alternating current loads, should not be placed in series. At least the AC loads we deal with. Here's what happens. T87F transformer, AT72D transformer, 24 volts output. Hook it up, all right, let the thermostat call, and you're going to get, that's what you're going to get. Because this is 24 volts, and if these 2 coils, solenoids, on these relays are exactly the same, you'll have a 12-volt drop across each of them. 24-volt coil ain't going to pull in on 12 volts. Any more than a 120-volt motor is going to run on 60 volts. Ain't going to happen. We don't put things in series. Put 2 zone valves in series. Neither of them are open. Parallel circuits. Here's a parallel. I got 3 parallel circuits here. Okay? Well, what happens to the voltage? Remember before it divided? Now it's the same. It's applied across each of the loads. If this is a 120-volt power source, then I'm going to have 120 from here to here, here to here, here to here. At any point I measure that. What happens to current? Well, the current's different for each device because your resistance is different even though your voltage is the same. And here's the math of it. And don't worry about the math in these last 2 slides. That's not important. Know the principles. The math is secondary. It really is. Now, that's what happens. I got a 12 volt, 6 volt, 4 volt. Now, what happens, or just the opposite, I'm sorry, what happens to the total current? The total amperage in the system? Well, it's the sum of the circuits, of each of the sum of all the circuits. In this case, I've got 3 parallel circuits, so it's the total of those 3. I had 12 amp here, I had a 6 amp here, and a 4 amp here. That's 22 amps. So if I read it here, I'm just going to read this amperage. If I read it here, I'm going to read that one and that one. And if I read it here, I'm going to read all 3. Depends on where you hook up. Resistance, that gets a little funky. Essentially, it's a reciprocal relationship. Okay? That the total, because this is parallel, remember it was 60 ohms in a series circuit? Here it ends up being 5.46 ohms because of this reciprocal mathematical relationship. Everything in electricity can be reduced to mathematics. And I'm telling you, don't worry about this because they're not going to ask you. And you ain't never going to apply that in the field in a million years. Open and close switches. If I have a power source, a closed switch, and a continuity through a load, and this switch is open, what am I going to read here? I should read 120 volts. I should read the applied voltage. Because when you hook up your meter this way, it's the same as reading from here to one side of power and the other way through this load, through the switch, and back to the other side of power. It's the same as putting your meter on either side of the source or the plug in the wall or the receptacle in the wall. How about this case? Same situation, but now the switch is closed. What am I going to read? I'm going to read nothing. If this is a good set of clean contacts, I should have no voltage drop from this point to that point. Because when you read voltage, you're reading a potential. You're reading one of 2 things. This is potential. All right? Let me explain that to you. Potential is the potential to do work. When you read this, or when you plug this meter into a receptacle in your house, and it says 120 volts, there's nothing else plugged into that receptacle. But you have the potential to do 120 pounds of work. or 120 volts electrical pressure of work. When you hook a motor into it and then you read across the motor, what you're reading is the voltage drop across that motor relative to the potential that created it. All right? Don't lose a whole lot of sleep about that, but I had to try to clarify that. In this case, I should read 0 because the voltage drop I'm reading is between the 2 points I'm reading. Back in this case, I read all the way from this side, back all the way around to the other side, and therefore I read this power. When I'm hooked up this way, there's continuity now because this is a closed switch, and I'm only reading the difference in voltage between this side of the contact and the other side of the contact. And that should be nothing. How about if I read a voltage drop here? What would that tell me? Well, I got pitting, or dirt, or a June bug got inside the contactor in the summertime at night because that contactor's hot from the current flow through it, and he decided he was going to sleep there that night, and the next morning the condenser contactor pulled in and he got squashed, and you got a voltage drop of 8 or 9 volts across there. Anything that shows a voltage drop means that there's something on those two contacts that connect each other to make this current, give this circuit continuity. Now, this case, we got an ohm meter. Open switch. This circuit then, because this switch is open, is isolated. What should I read here across this open switch? I should read infinity. It shouldn't move. This needle on an analog ohm meter should stay to the left. It shouldn't move. It should be near infinity. If it's a digital meter, it'll say OL, overload, out of range, whatever. Because your higher resistance is on the left side of an ohm meter. The lower resistance, the 0, is to the right. It's exactly the opposite of most analog scales. Now, in this case, same situation of isolated power by opening the switch, so it's safe to use the ohm meter, but what would I read across this closed switch? Well, digital meter is 0, analog meter should go hard to the right, dead short circuit, because I'm reading the resistance from here to here, which should be nothing. What would give me a resistance reading? A dead June bug, dirt, pitting. What is pitting? Let me explain pitting. Plug a small operational device into the wall, like a small desk fan. While the desk fan is running, jerk the cord out of the wall, and you're going to see a spark. If you don't see a spark, do it at night with the lights off. You'll see a spark, however small. That's because the circuit was made and you interrupted it by opening the circuit. And it was trying to maintain that, and it couldn't. As that plug got further away from the receptacle, the gap was too great, and what you saw was the end of electricity in the air. Okay, the end of current flow. Plug the fan back in, and don't turn it on. Have it off, but have it plugged in. Jerk the cord out the same way in the dark, and you're not going to see any spark, because there was no established current flow. You hadn't done that. Now, what happens in a contactor, and if you work on units, I hate to say this, in the dark at night, you will see that if you look at the contactors. As it opens and as the circuit opens, you'll see a spark inside where the contacts are. What I'm trying to tell you is every time a set of contacts open, there's an arc, because it was running a moment ago, and now that interrupted that path, and you get that little arc of current trying to go through the air and reestablish itself. Every time that happens, if you read the box, the paperwork, the contactor comes in, it'll tell you how many duty cycles it's good for, 2,000, 20,000, whatever the case is, depending on how good the contacts are. And what that means is that's how many times it can open and close before pitting starts, and you start to get a voltage drop or a resistance drop across it. If you have 1 volt drop or a 1 ohm drop, I'll say, across that contactor, replace it, because it may be running now, but it's on its way out. And pitting tends to become, corrosion tends to become exponential. You might have a 1 volt drop today, tomorrow it's going to be 2, a week from now it's going to be 4, then 8, then 16, and when you get up to around 12 volts, 10 volt drop across a contactor, you smoke the load it's attached to. The motor, the compressor, whatever else. That voltage drop is so great that it causes more than a 10% drop here at the load, and that will cause heat, so on and so forth, and it's heat that kills inductive loads. Motors, motor windings, hot, cold. The insulation expands, contracts, eventually cracks, it work hardens, and the windings short out to each other. And you go, oh, I got a short in my winding. Ammeter, of course, if the switch is open, you're not going to have any reading. This thing doesn't feel the intensity of the magnetic field until current is flowing. And if the switch is open, no current is flowing, you're not going to see any amp draw. In this case, it's closed, and of course you're going to read whatever the value is, 9 amps if that's a 9 amp motor, whatever. Pitting doesn't have anything to do with anything. It will simply cause a different amp draw here, which will be different than what it should be, that's all. Now, I want to show you the inside of this meter, only because I want you to understand that how important it is not to apply power when you have your meter set on ohms. Essentially, if you look inside of this thing, what you have is a permanent magnet. And this is the, let's say, a horseshoe magnet, and you're looking at the top of the horseshoe, not the bend. The bend is down the bottom. So we have a permanent north and south. Then we have batteries in series. And what happens to batteries that are in series? Their voltage adds. So if this is a 1, it's positive, negative, positive, negative, positive. So we got three batteries. If they're all, I don't know, 1.5 volts, then we have 4.5 volts, right? 3, 4.5. So if we send voltage through a conductor, and this is real fine wire wrapped around an iron bobbin, and we run voltage through a conductor, what do? We generate a magnetic field around the conductor. Now this needle, this analog needle, is connected to this bobbin. So if this current flow is great enough to overcome and create a magnetic field and overcome this magnetic field, then the needle will move to the right. If it's not, it'll stay to the left. So if I send out 4 volts out into this circuit out here, and 4.5 volts come back, all right, that's going to go hard to the right because I have my most power and I can overcome that resistance. All right. Now, if I send 4.5 volts out and no volts come back, the needle doesn't move because I can't create a magnetic field in here. And this is where your zero adjust, and basically what your zero adjustment is doing is correcting for how weak these batteries have become over time. You will find that eventually you zero this out as far as the dial will allow you to, and it's still not zero. That simply means it's time to change your batteries. Now, a good meter in this circuit somewhere will have a fuse so that when you do make the mistake of applying 24 volts to a 4.5 volt circuit, you don't smoke all the wire and destroy the internals of the meter. A cheap meter is what we call disposable. It doesn't have a fuse, and when you do put 24 volts or, God forbid, line voltage across a 4.5 volt circuit, you just let the smoke out of it. And when you let the smoke out of something, it doesn't work anymore. If you can keep the smoke in, it'll work. The same with motors. Very true. Continuity is defined technically as an ohm reading of 0 or a specific resistance. Either a dead short shows continuity or some value, some specific value that's not infinite. That is resistance. That is continuity. If you lack resistance, you're going to have infinite resistance, infinite ohms, if you will. Never connect an ohm meter to an energized circuit for the reasons I showed you. This internal circuit here, extremely light, extremely fine wire, okay, thinner than your hair. Electrical indicating devices. What are electrical indicating devices? Things like voltmeters. Question on the test is going to be, all right, how do you get a volt reading? You put a voltmeter on it. Okay, good. Now, how do you connect it? How is that voltmeter connected to this motor? And how is it connected to that switch? Well, it's connected in parallel. It's across the load. When somebody says put a voltmeter across that load, they mean exactly that, across the load, not in series with it. You put a voltmeter in series, you let the smoke out of the voltmeter. How's an ammeter connected? Well, ammeter's in series, isn't it? Always in series. You can't read amps if you're across parallel with the load. You have to be in series with the load. Now, if this is a 6 amp motor, I ain't standing there holding on to these two things with my hands. I'm either using alligator clips or I have this wonderful device called a clamp-on ammeter, which simply has to be tangent, perpendicular, whatever, to the flow of current. And it reads the intensity of the magnetic field. Ammeters for the test, always in series. Voltmeters, always in parallel. How about ohm meters? Well, they can really be anyway. They're usually in parallel. But the big thing with an ohm meter is disconnect power. The questions on a test, anytime you see any test, I don't care what you're taking, they ask you about applying an ohm meter, look for the answer that has disconnect power in it. Because if you don't, you're not going to get an ohm reading, you're going to get the smoke let out of your ohm meter. While we're on the subject of meters, this is what they call an auto-ranging meter. Ability of a measuring device, auto-ranging, means it has the ability of a measuring device to automatically select the appropriate range of measurement. You see here? You put it on volts, it'll decide whether it's AC or DC and whether it's 2 volts or 200 volts, whatever its maximum is. If you put it on ohms, it's straight up, that's not hard. If you put it on milliamps, it'll find the proper range. This is a maximum 10 amps. Okay, so it defines the range. You can't just hook it up and say, okay, automatically read volts and then automatically read amps. It can't do that. And this, by the way, is a digital meter because it has a digital readout. This is an analog meter because it has analog. Now, this is what they call a VOM, a V-O-M. It's a meter that displays volts, ohms, and milliamperes on the same scale. So depending on how you hook up the leads depends on whether you're reading volts, ohms, or milliamps. And it's analog. Analog has the dial, digital does not. They're going to ask you about all this stuff. What's a VOM? What's analog? What's digital? What's auto-ranging? All those things are going to be defined on the test. You need to know this. Why is this important? Well, what if you're going in to buy a meter and the guy says, well, you want digital or analog? You better know what you want. What if he says, you want auto-ranging or do you want the normal meter? What if you want RMS or a true RMS meter? You need to have this information. You're in an industry that requires that. Get up to speed. If I only have 2 wires on this drill and the housing is made out of metal and somehow I get an open winding or just one of the windings comes off and goes to ground, I've got to short to ground. Now, if I'm damp and I'm a good path to current, in fact, I don't even have to be damp in this case, if I'm a good path for current to go, because remember, it started out positive, it's hurting itself to seek negative, or started out negative and it's hurting itself to seek positive. Whatever the case is, current is going to flow to ground. And if I'm standing in the ground and I have continuity, it's going to go right through my hand. And God forbid, I got this drill in my right hand and my left hand is on some metal that's a good ground. Because then the current will go from right hand to left hand directly through my heart. And that's when we start having problems with, that's when line voltage kills you. 120 volt drill will kill you. So if I add this 3rd wire instead of the 2 I had here, and I have the same situation, now that metal frame that's connected to that 3rd wire is a better path for current than my damp body is. And as long as that's the case, the current will flow to ground. because that's where it wants to go anyway. It left this alternating circuit thing and left, let's say, positive, and it's looking for neutral. Or it left neutral, it's looking for a positive. Whatever the case is. It alternates every 1/20th of a second. If this housing is plastic, you'll see one of two things in the field. Either it'll be plastic with 2 wires, or it'll be plastic with 3 wires. Plastic with 3 wires is double insulated. You have the extra wire plus everything you touch is non-conductible. It won't conduct current, even if the current's leaning right up against the wall, the inside of that plastic housing. And of course, that's preferred. The idea, why do you ground any motor, any power tool, is to keep the housing at 0 potential. This housing is at 0 potential. Nothing's going to move out of that housing to a ground. This one wasn't. The potential here was 115 volts through your body to ground. You became part of the circuit. If you can keep this housing at 0 potential, what if you took your voltmeter and plugged it into a receptacle in your house and you read 0 volts? You got 0 potential to do work. As long as you can read from this housing to ground is 0, you're safe. If you read a voltage from this housing to ground, you're in trouble. And the higher that reading is, the more death-defying that becomes. Electrical symbols. We're flipping around, but that's what we do in this industry. We're flipping. All switches will reverse their positions when their coil is energized. Coils are shown in a lot of different ways. This is the one I like. This is Honeywell's idea of a solenoid or a coil, and if it was up to me, I'd put Honeywell in charge of all the schematics for all the wiring diagrams, low voltage wiring diagrams. Some manufacturers use this. When I see this on a set of plans, a complicated schematic for a unit, I'm thinking that's a motor, that's a load. Well, a solenoid is a load, but I just don't like motors looking like coils. Some manufacturers actually use the squiggle, and that's my best interpretation of that. It looks like the winding that it truly is. Because remember, a solenoid, regardless of how you represent it, is just a whole, maybe 500 feet of wire wrapped around, thin wire wrapped around some iron device that's going to intensify its magnetic field. So when I say all switches reverse their positions, that means that if you have a normally open switch like this, it's going to close. And if the switch is normally closed, it's going to open. So when this coil is energized and it's attached to part of this set of switches, this one's going to close. Close. This one's going to open. If you have a coil and then 2 sets of switches that are responding to it, this will close, that'll open, this will close, that'll open. Now, pole and throw. The pole is the amount of, the different power sources that can come into this. So I have single pole here. I can only have one power source. There's only one point to connect to. And the throw is the number of options you have on the outside of that, the output of that, if you will. So this is normally open. All right, so single pole, single throw, normally open switch. Here's a single pole, single throw, normally closed. All right, switch. That means unenergized positions. All switches are always shown in their unenergized positions. You have to envision, when you see this single pole, single throw, normally open switch, that when its coil gets power through it, and there's continuity in that coil circuit, that this switch is going to change positions. But when you look at it on the plan, it's going to show open. Okay, that's the way they're all going to show. Here's single pole, double throw. I have 2 throws. I have 2 options. I can use this switch for normally open. So when the thing calls, this will close, that'll open. This is my other option. This is double pole, double throw if they're mounted on the same base. I have 2 different power sources I can bring in, and each of those power sources has 2 different options of throwing. So it's double pole, double throw. If they're not on the same base, the other thing you can do is call that 2 single pole double throw switches. This is 2 of these. But if these switches are mounted on one base with one coil, then it's double pole double throw. Otherwise, single pole double throw. That's the way the switches work. They're shown unenergized, just like this. When their coils are energized, the switches change position. And this is a typical double pole double throw plug-in relay we use all day long, fan centers, whatever. All right, the coil is across 2, usually the double terminals. All right, that's the coil. One side of the coil gets hooked up to a transformer. Other side of that goes to a thermostat. Other side of the thermostat down the other side of the coil. In series, you have the coil with a power source with a switch that's going to close it and send the power through the coil. When the coil is energized, all these switches associated with that coil are going to change position. That'll close, that'll open, that'll close, that'll open. Whether you use them or not, it's going to happen. Other switches. You look at this, you should know that's a pressure switch. Looks like a bell, right? And the pressure is always from the bottom. Now, this switch, this is the switch, is above the line. So it's a high pressure switch. This switch is below the line, this line. So it's a low pressure switch. What's the action of this switch? It's going to open on a rise and make on a fall. This switch is going to open or break on a fall in pressure and make on a rise. High pressure, low pressure. You know what happens. This is in series with a contactor coil on your condensing unit. When the pressure in the condenser gets too high, it's going to open up. Save it. You know here that when the pressure gets too low, this switch is going to open up and save the compressor from low pressure. These are temperature. Picture this. This is a bimetal element. It's metal, okay? And if this were held down tight and you heated up this element, this would expand. It would open up. And the switch is above the line, so it's high temperature. This switch is below the line, so it's low temperature. Okay? This is a low temperature switch. You might use it for pump down or something. Or maybe not. Okay? Flow. Okay, this could be a flag. Could be in a water, could be a flag in an air system, like the old Honeywell sail switches we used to bring on the electronic air cleaners in my day. You use this one all day long. This is a float switch you use in a condensate pump. This is the second switch. The first switch, as the level rises, it makes and causes the motor to come on and pump out the reservoir in the condensate pump. If it doesn't, if the motor fails for some reason, the switch doesn't know that, but the level keeps rising, and what will happen then, it will open up, and it will make another set of contacts and cause a light to come on, or maybe you got the compressor Y leg broken across there. It'll shut the cooling off. Time is hard to show in a schematic, so they use the back or the front of the arrows. And it's usually shown open, but not always. And if you see arrows instead of something that looks familiar, it's a time function, and you have to know when that happens. You can't see it in the schematic. Humidity is always represented by a square, and I don't know why that is. I suspect that it has a lot to do with, in the old days we used, our humidistats and dehumidistats used balsa wood. Maybe that's what that is, just a square of wood, because balsa wood absorbs moisture very rapidly and causes it to swell, and when it starts to lose moisture, it does so at a similar rate and causes it to shrink back up again. So if you put this between 2 points and it expands, you'll make the circuit. As it contracts, you'll open the circuit. So I have a feeling that's where it came from. Safety switches are always shown normally closed. Control switches are shown normally open. If these two switches were shown closed, that means the switch is actually on the line, then they are high pressure and low pressure switches. If they're safety switches, in other words, they'd be in series with a compressor contactor to save it. They're safety devices. This is a heating thermostat because it's a control. Its switch is shown normally open. If it was closed, it would be a high limit probably in a furnace or something like that. This is a cooling thermostat. It's low temperature and it's open, so it's a cooling thermostat. If it was closed in this position, then it would be some kind of probably freeze device or something. It could be a freeze stat. You would put on a suction line if you were zoning a system and you had a bypass duct. If the small zone is open, that coil is going to get real cold real fast, so you put this in line, you put it on the suction line, it attaches and senses the suction line temperature. When the temperature drops too low, the switch opens and it kills power to the Y leg going outside. So the coil stays cold, fan indoor keeps running to get rid of that heat, if you will, in the coil, and the outdoor unit shuts off to keep the unit from getting any colder. As it warms back up again, it closes, and the contactor pulls in, and the outdoor unit starts running again, and nobody knows any different. Can't beat a freeze stat if you're zoning. Electrical schematics. These are schematic. They're also called ladder diagrams because of the runs in a ladder. Some things you need to know about them. First of all, the schematic or ladder diagram are used to assist the serviceman with troubleshooting and to determine the sequence of operation of the equipment. If I look at this device, first thing I want to do is find the transformer, because the transformer is the dividing line, and it wouldn't matter if this whole thing were turned flat and the transformer were in the center. I'd have low voltage on the right and line voltage on the left, or tilt it the other way. It doesn't matter. But this is the line of demarcation. Everything above this, in this particular case, is line voltage. All these devices and switches. Everything below this transformer, in this case, is, because it's a step-down transformer, is low voltage. So I can just look at this and say, oh, it's a what is that, indoor fan motor, and this IFR-1 switch is in a line voltage circuit. It should be right in the common line to this fan. Know that the vertical lines, if the schematic is in this position, or the horizontal lines if it's turned sideways, but if it's in this position, these lines represent power. Here's the line voltage, L1, L2. This is 240 volts, 110 to ground, 110 to ground. Here's the induced secondary current, 24, 24. It's not grounded, so this is one side of 24 induced, this is the other side of 24. It's not going to be 24 to ground because there is no ground. But know that the vertical lines in this case are power sources. Now I can look at this thing and say, well, here's my reversing valve relay, and it's in series with a thing they're calling 1 TSH. So that's TS is thermostat, H is heating. So the reversing valve, and this is above the line, so it's high temperature, so that makes sense that looking at this thermostat is the first stage heating. Because right down here, here's a heating thermostat that says 2 TSH. So that's a second stage. All right, this is S, so it's probably O rather, so it's probably an outdoor thermostat. Here's a cooling thermostat. So I know my reversing valve by looking at this diagram. If I study it for a minute, I can figure out that the reversing valve is energized in the heating mode. Good information to have if you're dealing with a heat pump. If I didn't know what RVR was, I go to the legend. And the legend, they're going to ask you about in a test, defines all that stuff. RVR is reversing valve relay. RVS is reversing valve solenoid. That this heavy dashed wire is field supplied line voltage. This is factory supplied line voltage. It's solid. That low voltage field supplied is light dashed wire on the schematic, and then the solid wire you see in the schematic is factory supplied low voltage, but it's thinner than the line voltage. They're going to ask you about this in a test. And this is very common, and unfortunately there's no rules on low voltage and how it should be represented or what the symbol should mean. It's chaos. So you will see deviation from that. Very often dashed lines mean that something is ganged. That, when you throw the system switch into cooling, you automatically put Y and G common. All right, that kind of thing. Pictorial, that's schematic. That was the legend. Pictorial diagrams simply show you a picture of where the controls are in the system. If you open the door to a complicated device, if they have a pictorial diagram and you're looking for the reversing valve relay, oh, it's right up top. There's 3 relays together. It's the one on the left. That's how you would find it. You want to know where the defrost relay is? Oh, it's right below that stack here. Yeah, that kind of thing. Where's the contactor? Oh, it's in the bottom right corner of the control panel. Where's the second outdoor thermostat? Oh, it's on the right here between these two. You know, that's all it's for. Doesn't tell you when the reversing valve relay is energized. It just tells you where it's located in the system. This is a connection or a hookup diagram, they call it sometimes, that the installers want to have so they know what size cable to bring. From here to the compressor, I need a 3-wire. You know, then I need a 4-wire up here, and out of the transformer, I need 5 wires going to the thermostat, that kind of thing. Here's the reversing valve relay again, but you can't tell from looking at this whether it's energized in the heating or cooling mode. The schematic tells you that. So those are the 3 kind of diagrams: ladder schematic, pictorial, and connection diagram. We use the schematic diagram primarily. Feedback potentiometer, very quickly. I don't want to beat this to death, but that's what one physically looks like, if you will, that attaches to the motor. And what they do, a feedback potentiometer provides proportional control, is the key phrase here. Proportional control to the device, the motor that drives the valve or the damper, you know, the steam valve, the hot water valve, whatever the case is. Let's say you've got a heating system, a hot water heating system, and it's a commercial building, and you've got a open-close valve. That's it, what they call a 2-position valve. It's either wide open or completely closed. There's no in-between. A feedback potentiometer gives you in-between. Go back to that 2-position valve, and you walk in the building in the middle of the afternoon, and it's calling for heat, and the room thermostat is set for 68, and the room just dropped to 67. What's going to happen to that 2-position valve? It's going to open up wide, completely open, and it's going to flood that hot water coil, especially if that's a 3-inch valve. It's going to flood that hot water coil with mucho gallons per minute flow. And the result of that is going to be you're going to overheat the room because you just got that blast of heat, hot water in that coil. That's going to bring the fan on. And even though it'll take a minute or two for the thermostat to sense that heat, by the time it shuts down, that coil is completely overheated. And the result of that is the room is going to be completely overheated. So if you're tired of those kind of inefficiencies and you're willing to spend the money to convert those valves to proportional control, then you're going to employ a feedback potentiometer. And the feedback potentiometer will look at the thermostat demand, and it's going to look more at the differential, room relative to demand temperature. You demand 68 degrees and the room dropped to 50. All right, open the valve most of the way. Okay, the room is demanding 68 and you drop to 65. Well, open the valve about a quarter of the way. You know, that kind of thing. That way you don't overheat. All right, you maintain a simple efficiency just by regulating just like a TXV valve does. When you got a 20-ton unit, you got one TXV on one circuit, and it's in a church, and it's Sunday, and the door's open, and it's hot out, and 200 people walk in and sit down. That valve's wide open. But when it's Friday night, and it's just 20 people from the choir in there practicing, and you have a 1-degree call for cooling, the valve doesn't open up that wide. It just starts to migrate open. It starts to allow a small amount of refrigerant into the evaporator relative to the load, because it won't take a lot of time. If it did open wide, it would shut down quickly, and that would create, that's hunting. That's when a valve is oversized. Wide open, floods the coil with cooling, and then boom, shuts down, right? But these feedback potentiometer works very much like a TXV valve does. GFCI, or as you probably know it and love it, GFI. We don't get the circuit in there. It's a ground fault circuit interrupter, GFCI. All right, you can have the receptacle type. You can buy the inline type. You plug into, your extension cord or whatever, and then plug the device into that. It's an electrical device which protects personnel by detecting potentially hazardous ground faults and quickly disconnecting power from the circuit. And I mean quickly. A GFCI compares the amount of current in the ungrounded, the hot conductor, with the amount of current in the neutral conductor. They should be what? The same, right? If the current in a neutral conductor becomes less than the current in a hot conductor, where is it gone? Well, it's gone to ground. This is electricity. It's very definitive. 6.24 times 10 to the 18th power. Oh, wait a minute, there's two of them missing. Oh, they went to ground. So if we just compare, the hot to neutral, then we know that we have a ground fault. And anytime current flows to ground, it's a fault. It's not a good thing. Something went wrong, and now we're faulting that current flow. The amount of current that is missing is being returned to the source or to the earth by some path other than the intended path, the fault current. A fault current as low as 4 milliamps, that's 4,000th of an amp, to 6,000ths of an amp activates the GFCI and interrupts the circuit. So this device protects people from going to ground. You know as well as I do that all the kitchens, bathrooms, if you have an outlet in a kitchen or a bathroom, around a pool, anywhere where water exists, and you could use that outlet with a device and come in contact with that water, NEC requires a GFI or a GFCI. Thank you for your time and attention. Again, I know how important that is to you, time especially. There's just not enough of it in a day. So let's do a little Q&A. Number one, electricity is the potential difference between negative and positive poles, the induction of voltage through a resistance, the flow of electrons through a conductor, all of the above. No, it's the flow of electrons through a conductor. I mean, this might be tempting, but the potential difference between two poles is, the best you could define that is voltage. And inductance, you don't induce voltage, you induce current that creates voltage. Anyway, number two, voltage in an energized electrical circuit can be thought of as electrical pressure, electrical resistance, electrical flow rate, electrical volume. What is voltage in an energized electrical circuit? It's pressure. All right? It's really pressure in an unenergized circuit if it's potential. 3. How is current flow measured in an electrical circuit? How do you measure it? With a voltmeter, an ammeter, an ohmmeter, a megohmmeter. Well, which of these devices do you measure current with? Ammeter. Amps is current, which is electron flow. Amperage, current, electron flow, all the same thing. Coulomb, whatever you want to call it. They're all the same. They're all equivalents. A milliampere is 1/10 of an ampere, 1/100th of an ampere, 1/1000th of an ampere, 1/1,000,000th of an ampere. What's a milliampere? 1/1000th. Whenever current flows through a conductor, it will cause the voltage to peak before the current. The resistance will cause the current to peak ahead of the voltage. A magnetic field will be canceled out of the rising current, or canceled out by the rising current, or a magnetic field will be established around that conductor. Whenever current flows through a conductor, what happens? Magnetic field is going to be established or built up, developed around that conductor in the form of magnetic flux lines. If a conductor is moved through a field of magnetic flux, what happens? A permanent magnet will be created in the conductor. The resistance of the conductor will be eliminated. a current will be induced in that conductor, or a current will be established in the magnetic flux lines. What happens when a conductor is moved through a magnetic field? A current is induced in that conductor. 7. In an induction transformer, the winding that receives the source voltage is called primary, secondary, mid-tap winding, common winding. Which of the windings gets the source voltage and source current? Primary winding, you betcha. 8. If the primary voltage on a step-down transformer is 110 volts and there is a 5-to-1 turns ratio, what is the secondary voltage in this step-down transformer? 110 in? Is it 18, 20 volts, 22, or 24 volts? What's the secondary voltage going to read right at the transformer? Okay, well, the secondary voltage is equal to the primary voltage, which in this case was 110, divided by the turns ratio. 110 divided by 5 to 1, is 22 volts. So we can expect to see 22 volts on our digital voltmeter, plus or minus the accuracy of the meter. Given a domestic hot water heater with a 4500 over 4500 watt element and a non-simultaneous operation, all right, this is as common as it comes. The electric element for a hot water heater is almost always going to be 4500 over 45 non-simultaneous, meaning both of those 4500 watt elements are not going to run at the same time. You can wire any heater for simultaneous operation, but you better have the breaker you need to do all that and the wire size you need to do all that. So given this situation, what is the anticipated amp draw of an energized element when there's 220 volts is read at the element? Okay, well, 18 3/4, 20 1/2, 30.68, or almost 41 amps. What are you going to read? You can determine this easily. All right, get this out. What are we solving for? Amperage, isn't that what they're asking about? What are you going to do? You're going to divide the voltage, which we know, into the wattage, which is given. So if, in fact, we're using 4,500 watts, we can divide P by E, 220, we can expect to see 20.45 amps on our amp meter or our clamp-on ammeter. 10. Given a half horsepower blower motor that draws 6 amps and 118 volts during operation. Half horse blower motor, 6 amps, 118 volts. A wattmeter is then connected and shows a reading of 638 watts. What is the power factor for this circuit? Well, take all the numbers. You know, it's either 70, 80, 90, or 100% efficient. How efficient is this circuit? Well, power factor is watt reading, actual power, divided by apparent power. Okay, so we read 638 watts in our wattmeter. We're going to divide that by 118 volts times 6 amps that we actually read. 0.9. That circuit is 90% efficient, essentially, is what we're saying. 11. A diode in an electronic circuit. A, amplifies current flow, suppresses current flow, allows current to flow in both directions simultaneously, or acts as a conductor in one direction and as an insulator in the other direction. What does a diode do in an electronic circuit? Yeah, acts as a conductor in one direction and an insulator in the other. Only allows current to flow in one direction. 12. What happens to the voltage in a series circuit? What happens to it? Does it divide across each of the loads? Is it the same at any point in the circuit? The voltage will always lead the current in those circuits, or the voltage will always lag the current. What happens in a series circuit to voltage? It's going to divide across each of the loads. That's what gives you the chattering in a if you put 2 contactors in series, or 2 relays, or 2 loads in series. 13. What happens to the current in a series circuit? It divides across each of the loads. It's the same at any point in the circuit. The voltage will always lead the current, or the voltage will always lag the current. What happens in a series circuit to current? What happens? Well, it's the same at any point. The same current flows through all the loads in series. The voltage is the thing that drops, and therefore it can't work. The pressure's not right. Look at it that way. 14. What happens to the current in a parallel circuit? The current, the amperage in a parallel circuit. It divides across each of the loads. It's the same at any point in the circuit. The voltage will always lead the current. The voltage will always lag the current. What happens? Yeah, it divides across each of the loads. It's different depending on the load. This is parallel now. What happens to voltage in a parallel circuit? Well, it divides across each of the loads. It's the same at any point in the circuit. The voltage will always lead the current. The voltage will always lag the current. Which is it? Well, it's voltage. It's a parallel circuit. It's the same through each of the circuits. 16. What should the voltage reading be across a good set of closed contacts in an energized circuit? You got a closed contact, they're good. What should the voltage reading be? Should it be counter EMF? Should that be the value? Should it be the line voltage? Should it be the applied voltage? Should it be 0 volts? What should you read across that set of contacts? Yeah, you shouldn't read a thing. If they're good, you're only reading a voltage drop across the contacts. It should be 0. 0 volts. If you read 1 volt, 2 volt, whatever, replace the contactor, the relay, whatever it is. It ain't going to last. It's starting to pit. 17. What should the voltage reading be across a good set of open contacts in an energized circuit? Now the contacts are open, same circuit. Counter EMF, line voltage, the applied voltage, 0 volts. What should you read? The contacts are open. Applied voltage. You betcha, puppy. 18. What would cause a voltage drop across a set of closed contacts? What would cause that? All right, a voltage drop. Use of a non-RMS meter, root mean square meter. A capacitor circuit would cause that. Pitting or dirt might cause that. This is a normal reading across a closed set of contacts. What's the best answer here? Yeah, man, better be pitting or dirt, something like that. A June bug. 19. Continuity refers to a circuit with all switches closed. A circuit with all switches closed and all loads connected. A circuit with no capacitors and no inductive reactance. A continuous, uninterrupted circuit. Of all this junk, what's the best academic answer you can see here? Continuity is what? A continuous, uninterrupted circuit. That's where the word continuity comes from, the root continuous. Or vice versa. I don't know whether the egg or the chicken came first. 20. What is the most important thing to remember when applying an ohm meter to an electrical circuit? What's the most important thing? Make sure that the power source is disconnected before connecting the meter. Make sure that the meter is properly calibrated for the reading to be taken. C. Be sure to zero out the meter before connecting to the circuit. Or D. Observe correct polarity when connecting the probes. Now, I'm not going to be here to do this for you, but what did they ask you here? What's the most important thing? Well, the most important thing should be obvious. Make sure the power is off, because if it's on, none of this matters. You're not going to have a meter to deal with. 21. How should a voltmeter be applied to a circuit or load? How should it be applied? In series? In parallel? From hot to ground? From hot to neutral? How do you apply a voltmeter to a load or a circuit? Yeah, in parallel. You've got to be across the load or the circuit. You might be hot to ground. You might even use it going from neutral, hot to neutral, to look for something, look for voltage or whatever that shouldn't be there, or hot to ground rather. But, when you apply it in parallel. And when you are hot to ground, you are parallel to the circuit. All right? 22. How should an ammeter be applied to a circuit or load? In series, in parallel, from hot to ground, from hot to neutral. How do you apply it? Series, of course. Ammeter has to be in series, not an amp probe. Amp probe, by the way, is the name of a company that makes clamp-on ammeters. Amp probe was one of the first companies to come out with it. They make all kinds of electrical devices, indicating devices. And they're a good company. They're a great company. They were the first with the amp probe, the first to be popular. And everybody called that little black clamp-on ammeter an amp probe because that's what it said in big red letters on the amp probe. So I even call it an amp probe to this day. But know that that's the name of the company, not the device. 23. An auto-ranging digital meter will automatically select volts, amps, or ohms, select the proper polarity for the probes, select the proper range of measurement, select the appropriate range of cycle rates. Well, what is an auto-ranging digital meter going to do? It's going to select the proper range of voltage, amperage, whatever you set it on manually. 24. Which of the following best describes a VOM, of ohm? A digital meter that displays volts and ohms on the same scale. A digital meter that displays volts, ohms, and milliamps on the same scale. C, an analog meter that displays volts and ohms on the same scale. And D, an analog meter that displays volts, ohms, and milliamperes on the same scale. What's a VOM? Well, it certainly isn't a digital meter, or it couldn't show three things on the same scale, because you only get one scale on a digital meter. So obviously it's an analog meter, volts, ohms, and milliamperes. 5. Why are the frames of electrical devices grounded? Why do you ground the frame of an electrical device? It's an OSHA requirement to keep the frame at zero potential, to prevent a short circuit. According to NEC, all plastic frames must be grounded. What's the answer? NEC's National Electric Code. To keep it at zero potential, right? 26. What is the action of this switch below? Here's the switch. What action does that switch take? All right. Closes on a rise in temperature, opens on a rise in fluid level, closes on a rise in pressure, and opens on an increase in humidity. What action does that... When you look at that switch on a schematic, what comes into your brain? What should pop into your brain? Yeah, it's a low pressure switch. And it's a control. It shall normally open. And when the pressure gets high, it's going to close. And when the pressure gets low, it's going to open. Okay? Make, break, open, close, similar. 27. Which of the following electrical diagrams would a service technician use for troubleshooting a system? Schematic wiring diagram, pictorial wiring diagram, connection wiring diagram, electrical wiring diagram. Schematic. Hopefully schematic, they're called ladder diagrams. Okay. 28. What is the function of a feedback potentiometer in an electrical circuit? Allows for two-position control of an inductive load. Causes a motorized valve to be either only fully open or fully closed. Sends a feedback signal to the thermostat to calibrate the temperature setting, or provides proportional control to a motor that drives a valve, a damper, whatever the motor is connected to. What does a feedback potentiometer do? Yeah, provides proportional control. 29. Which of the following is field installed line voltage wiring? A, B, C, or D? Which is field installed? Got to be dashed. Which is line voltage? B or D? Yeah, man, B. Number 30, a GFCI is an electrical device that protects users from dangerous ground fault currents, or circuits, currents, whatever, is used to isolate a low voltage control from a line voltage loads, acts like an induction transformer in a DC circuit, converts full wave AC to full wave DC current. What does a GFI, GFCI do? Yeah, protects users from dangerous ground fault currents. You, the user, hopefully a protection. Hopefully we'll see in part 3. Now these questions we just went over are very, I made them pretty straightforward because what I wanted you to do was rethink about, maybe in another way, about what I presented to you just previously. And I even went in the same order. I gave you a question in the beginning of the question Q&A section that was in the beginning of the presentation, and the ones in the middle were in the middle, and the one at the end was at the end, as you remember GFCI. But ain't going to be that pretty, that sweet on the exam. All right, you're going to have a whole lot more mumble jumble. So expect it. Prepare for it.